So, this is in brief about multi-channel analysis of surface waves. Now, let us look into some case studies. What are all the applications? So, here is a result obtained by this company in which they had conducted the multi-channel analysis of surface waves at a site mainly to characterize the bedrock. Right. We are going to see little later how rocks are classified based on the shear wave velocity. Right. What does it indicate? When the velocity of the shock waves are higher, obviously rocks are solid, more massive. Right. When the velocity of shock waves are much lower, the rocks are very weak. Hence, we are able to get a nice idea about the subsurface after arriving at a cross section of the velocity. So, here you have a beautiful cross section of the velocity distribution below the surface of the earth. So, from the scale, all the blues are low velocity, very low velocity. All the reds are solid rocks. Velocity is already almost 1000 meter per second. So, this is how we are able to characterize the subsurface. So, at this place we can say only up to about 20 meters we have weak soil. Beyond that we have mostly a weathered rock, probably a weathered rock, but the velocity is nearly 1000. So, this is how we can use MOSFET to characterize the basement rocks to decide whether what kind of foundation we can plan for constructing a major building at this site. So, here is another example from the same company, right? Here they had assessed the subsurface conditions for planning for a huge windmill. So, windmills have to be anchored at sites where the ground surface is intact because it is a huge structure. It will create lot of vibration too as these wind blades will rotate. Here MOSFET has been carried out in several profiles as I was drawing earlier, right. Since we have got sections at several profiles, right, you can have vertical sections wherever you want. What does it show? It shows as usual the velocity profile, right. So, velocity profile we got at several sections in vertical direction, let us say xy direction, or in other words north south. In north south direction we have the sections arrived at different locations. Now, we can also do interpolation. In what way? I will take one line here, 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 and arrive at a section, horizontal section, right. Similarly, you can take one line here, one line here, one line here, combine them and interpolate the in between missing locations, and then we can arrive at a, this is north south, this is west to east, several sections we can arrive. So, this is how by conducting multi-channel analysis, by conducting seismic survey in several closely located profiles, we can three-dimensionally characterize the subsurface. So, here you see a three-dimensional diagram showing the velocity distribution. That means all the red part, they are of high velocity region. So, even at the surface you have some locations, part of your area is having very high velocity, nearly 2000 meters per second. sound rocks, massive rocks, right? And you can also even slice and see how the velocity varied inside, right? The software has got that ability to slice different dices to understand how the velocity is distributed within this cuboid, right? So, this is another application of MASVA. In the next application, these researchers are conducted a study using multi-channel analysis of surface wave to evaluate groundwater resources. Not only on this, they had also used some other techniques. I think they have used GPR, also some borehole drilling, groundwater level measurements. But here they have showcased how multi-channel analysis is able to bring out the subsurface geological conditions as well as groundwater conditions in Spain, right? Here what they have done, similar to the previous study, they had conducted multi-channel seismic survey at a site at several profiles, and then they arrived at dispersion curves, and then they had gone ahead with the inversion. What you see is the inversion sections showing you the velocity distribution, right? Here the white color are all the reds, you don't have anything here, always the reds are nearly 1000 meters and the light blue colors are 100 meters. So, here you can see the sections prepared by multi-channel analysis is able to delineate different zones, right? Top zone of up to about 8 meters, right? Here you can see there is a different color, right? And you can also see the water table has been plotted, right? Or the piezometric, that is the water table they have plotted here, right? And you can see the section at different locations, the velocity above and below is different, and wherever there is a major change in the velocity, probably indicating the change in the type of rocks. Certainly, isn't it? Velocity will be high only in massive rocks. So, based on the velocity distribution in all these sections, they have deciphered the subsurface geology. The uppermost has a velocity less than about 300 meters, that is 1 to 8 meter thickness. Then underlying that is about 2 to 10 meter thick with a velocity greater than 350, right. Beneath that is another third layer of 10 to 15 meter thickness where the velocity varied between 300 to 600, right. And they had also found out the next layer where the velocity is much higher. Velocity is nearly 1000, that is 900 to 1200. The velocity varied 900 to 1000 and very deep velocity was greater than 1200. So, this is how, right, somewhere here this zone is very high velocity zone, almost of this color, right. So, this is how from the velocity distribution different layers were deciphered and also making use of some geological information available from that site. On the velocity section they have also indicated, right, the top zone is filled material, right. That means a low lying area has been filled, maybe in the past they had filled it, that could be deciphered. So, here you can see they have written anthropogenic filling, this particular zone, a small zone, right. Then river delta could be demarcated, right? In this section they have written the different names, right? Where is the river delta, Holocene river delta, that is the alluvial formation. Alluvial formation, then we have anthropogenic filling, here too anthropogenic filling, that means subsequently people have filled. Then different zones are demarcated, right? Right. T1 is the littoral phases. Then you can see WB is the weathered and fissured rocks, right? BE is a crystalline bedrock, BE, WB, these are all massive rocks. So, beneath this you have massive rocks. So, this is how from the velocity variation we are able to identify major rock types. Not only that, the MASWA is able to bring out major geological structures. You can see, right, especially this one is very interesting, right? Here you can see there is a marked change in the level, indicating this part of the earth has moved downwards with respect to the rock on the left hand side. You can literally see something like a staircase here. The velocity distribution is able to show us a major structure, which is a fault. Fault, as I told you previously, fault is a plane along which blocks of the earth has moved over, right? Like a shear, right? This has moved downward with respect to the one on the left hand side. So, faults were also demarcated, right? Here, right here too. So, faults could be identified using this technique. Right? This is one of the application of multi-channel analysis of surface waves. In another study, they had combined, in the previous study they had made use of ground penetrating radar too. Here, a study carried out in Portugal, they had made use of combination of resistivity method, electrical resistivity method, that is earth resistivity tomography, coupled with MASWA, right? These researchers have carried out a study, right, which has brought out very clearly the subsurface cross section at different locations, right? These are the locations wherein they had carried out a study, right? As in the previous case, here too faults were clearly demarcated, right? They had they had found out faults at number of places, right? This is observed as well as deduced. This is an inferred fault. That means from MASWA we were able to infer a fault, right? Observed, deduced, contact, inferred geological contact, and this is water table. So, water table is also, this is the top line, this line is the water table which is continuous throughout. From the velocity distribution we could decipher three different rocks. The rocks beneath this is very kind of massive rock with the velocity nearly 1000. Then the next zone colored in blue where the velocity varied between 200 to 450. The top zone, the velocity is about 50 to 150. So, this is how we could differentiate three major rock types, right, and their depth were also estimated by them. Right. This study has been was carried out mainly to understand whether the coastal groundwater is able to manage the ecosystem. That was the aim of this study, right? The study brought out the subsurface geology as well as the location of faults, right? Here, since no data was available, this part is left blank, right? This is another application of MASWA. Then in this study, they try to understand the subsurface site conditions by arriving at the velocity at 30 feet below the surface. Right. Here the survey was carried out using a land streamer. That means, hope you can recollect, when we had seen seismic operation on sea, right, the ship is continuously moving and all the receivers are towed by the ship, they are floating. These are all the receivers which are called as hydrophones in the case of a ocean survey. The ship is continuously moving, we keep on repeating our survey. So, the entire profile is continuously studied, several kilometers are continuously studied, because we will be using some energy source, usually air guns. Air gun will fire, work will be over. The ship would have moved, next, like that we will progress. Same thing is also possible on the land by having the geophones fixed on some nice kind of cables or tubes. Usually here they are using a fire hose. Why are we using such a hose is the energy may not be transmitted within the hose, right, because these hoses are energy absorbers, right. So, whatever shock received by the geophone here will not be transmitted, because it is a kind of flexible pipe, right. And to this hose pipe we attach the geophones, right. That means geophones are not having any spikes, it is not going to have a firm contact with the earth. So, some signals will be lost, but to compensate for that we may add some weights around the geophone, so that the geophone part of the hose pipe is firmly resting on the ground surface, right. That means this is the pipe, hose pipe, to which we have attached a geophone receiver and the next receiver. Around this we may add some weight, right. Weight may be in the form of maybe a steel plate, right. It can be maybe a steel chain will be kept around that, so that the hose pipe, the geophone firmly touches the, that is the aim, ground surface, right. What is the advantage of such a land streamer? You can rapidly carry out the survey, because every time you need not pull out the geophone, plug it again, right, because it is attached to a streamer, it can be connected to a vehicle, you can continuously move. The vehicle may also have a weight dropper, right. So, drop a weight, survey is over, then pull the streamer. So, you can carry out investigation for a long profile at a shorter time. So, that is what they have done, right, by carrying out this survey. So, first they had identified, they have understood the dispersion curve. From there, first they have initialized a model by assuming some parameters, that is the yellow line, right. That yellow line is the model assumed variation in shear wave velocity at different depths. So, this is depth versus velocity, and then they carried out the inversion process several times. Finally, they arrived at a result which is shown in red color. What does it indicate? At whatever result they got when they assumed the shear wave velocity as shown in red color, that would have been matching very well with the field derived data. Okay, so the red is the model derived data. Why we said red is the final one? Because here it would have matched with the field observations we have made using MASFA, right. So, these are at two different locations. As an example, I picked from their publication. I am showing you for the benefit of you to understand the application, right. On the right hand side, we see the velocity distribution nicely brought out for the entire stretch of nearly half a kilometer up to a depth of about 40 meters. Then from here they picked out the velocity at a depth of 30 feet, that alone has been plotted separately. How the velocity Vs30 varied along a profile. It was almost around 300 meters. Why Vs30? Right. It is internationally accepted, right, as per the National Earthquake Hazard Reduction Program, right, NEHRP, right. According to them, the rocks are classified based on the velocity of the shear waves at different distances below the surface of the earth, right. So, it is Vs30 here refers to Vs velocity of shear waves at 30 meter below the surface of the earth, right. So, if the velocity is greater than 60, then the rocks are considered to be very hard, right. If the velocity is of this range, it is considered to be still it is a rock. If it is of this range, soft rock, this is soil, very soft soil, less than 600, right. So, this is how we classify the rocks into different categories based on the shear wave velocity, right. So, here the velocity is given in feet per second and here we have in meter per second, right. So, broadly we classify a rock as a hard rock when the velocity exceeds 1500 meter per second. When the velocity is around 300, it is classified as a dense soil. So, which means in this case it is around 300, so it is a dense soil. What is the purpose of this classification, right? Generally, it is understood the characteristics of the material that are present until 30 meters from the ground surface is very crucial, because that is going to be the zone where in the event of any major earthquakes, the seismic energy will be dissipated through this zone of 30 meters, where the ground vibration is going to be amplified based on the nature of rocks that are present in the top 30 meters. So, based on that, this agency has classified the rocks, right. Suppose if the rocks are of this nature, then during any tremors, the buildings are not going to be very much affected. But if the rocks are having a velocity of only less than 200, the seismic signals during earthquakes, seismic shocks will be very much amplified, and the liquefaction can lead to disasters. So, that is the idea of this classification. So, by multi-channel analysis of surface waves, MASVA, we are able to categorize the rocks as per this NEHRP classification. That is another advantage of multi-channel analysis of surface waves. Then in the last case study, these researchers have carried out an investigation in Nepal, right, to understand the characteristics of rocks at near surface, nearly about 30 to 40 meters, to see whether the site is suitable for constructing a tunnel, right. In this study, they had used both MASVA as well as MAM, which is a micro tremor array measurements. It is like passive method. This is active. We are going to energize the ground. By carrying out this investigation, they have arrived at how the shear wave velocity varied with respect to depth. So, here is the velocity with respect to depth and how frequency is also related. And they had compared their findings with the borehole logs that are available at that site. So, here they could classify the rocks and assign the rocks for different velocities. So, here the velocity is nearly 900 meter per second, here it is about 800. At the top we have very loose soil with a velocity of only 150 to 200 meters. So, this is for one site, this is for another site. So, this is how they had made use of MASVA to characterize the subsurface rocks to assess the suitability of the site for tunneling purpose. So, these are all the different case studies that highlights the application of MASVA. So, in this lecture, we had seen the third major seismic method, which is multi-channel analysis of surface waves, which makes use of Rayleigh waves. Right? We had seen Rayleigh waves are of dispersive in nature. That is what we make use of. The sources of the same, we had seen what are all the sources that can be used, and receivers are the conventional geophones, that is vertical component geophones are used. How are we carrying out the method? Also we have seen the method of seismic survey is the same. The data analysis is different. First we do dispersive analysis. After that we do inversion. After inversion we arrive at the subsurface sections, or we arrive at a relation between velocity versus depth. So, we are able to arrive at in a cross section showing the velocity distribution, and toward the end we had seen some applications, we had seen some case studies. I am sure this would have enriched you on the versatility of multi-channel analysis of surface waves. Thank you.